The purpose of this lab is to observe the effect air resistance has on a free-falling object by comparing two models of free-falling systems, one with air resistance and one without air resistance. The lab followed the following steps. Step 1, video recording. Step 2, data extraction. Step 3, model creations. And Step 4, observation and model comparison. The result was that the model with air resistance closely mimicked the observed data, while the model without air resistance significantly overestimated the distance traveled. Onto the model. The model created is a time versus position graph in which the x-axis represents time and the y-axis represents position. The blue line represents the data from observation, the orange line represents the model without air resistance, and the gray line represents the model with air resistance. The three lines are overlaid for comparison. The first main physics idea used is velocity and momentum. Velocity is a rate of change in an object's position with respect to the amount of time passed. Momentum is a vector quantity calculated by multiplying the mass and velocity of a system. And according to Newton's second law, the change of momentum divided by the change in time equals the net force acting on a system. Secondly, the formula for gravity is gmm over r squared. And since we are near Earth's surface, we are assuming that the gravitational acceleration is 9.8 meters per second squared. Air resistance in this case is represented as a constant times velocity squared, as air resistance is proportionate to the square of velocity. And onto the experiment. A video of an umbrella falling was recorded during the week 4 lab meeting. A ruler was placed next to the wall to use as reference. And in this case, the system is the umbrella. The surrounding is everything in the room excluding the umbrella, such as the air. Initial conditions were starting position 0 meters, initial time 0 seconds, and initial velocity 0 meters per second. Then tracker was used to extract the object's position and corresponding time, which was then made into a table and graph. Onto the code. GlowScript was used to create a computational model that resembles the observed motion. Assumptions that were made to create the model were first, mass of the system 0.3 kilograms, which is the weight of the umbrella. Net force acting on the system equals F gravity minus or plus F drag, as we are assuming that there are no other forces acting on the system. Third, the system comes into frame at 0.167 seconds and moves outside of frame at 1.302 seconds, according to the timestamps on tracker. And last, constant for drag force is 0.522, as it gave me the best results. Now to the code. Line 36 was altered for the mass, line 40 for initial velocity, line 43 for start time, line 65 for start and end time, line 70 for force, line 74 for acceleration, line 76 for velocity, and lines 90 to 94 for the arrow. This shows the final model without air resistance. The top left shows a model resembling the movement of a system with an arrow representing gravitational force. The bottom left shows the time versus position versus time graph, and the top right shows the velocity versus time graph, and the bottom right shows the precise position of the system as time increases by 0.001 seconds at a time. The only difference for this code is line 56, which is the constant for air resistance. And this is a final model for air resistance, and you can see that the only differences are in the outcome, the arrow for drag force pointing upwards on the top left, and the velocity versus time graph being nonlinear. For the final graph, the data from tracker and GlowScript were input into tables in Excel, and those tables were then used to create a graph comparing the 3 sets of data. The similarities are that all 3 graphs suggest that the system moves towards the negative y direction. The observed data and the model with air resistance have similar start and end values. The differences are that the model without air resistance has massively different data compared to the other two, and the model with air resistance slightly overestimates movement between 0.4 and 1.2 seconds compared to the observed data. Now to discussion questions. The possible rooms for error were unstable recording, umbrella not falling directly in the negative y direction, inaccurate clicking on tracker, and bad video quality. What does it mean? The model with drag predicts a terminal velocity as a velocity on the model. With drag eventually stops increasing, while that is not the case for the model without air resistance. And since velocity doesn't change, this means that the net force acting on the system is 0 at terminal velocity, as the magnitudes of gravitational force and drag force will equal each other. What if, even if the object is initially thrown downward, terminal velocity will be the same as when the object is dropped from rest, as a velocity in which the drag force equals the gravitational force will not change. The graph on the left shows velocity versus time when the object is dropped from rest. And the graph on the right shows velocity versus time when the object has initial velocity of -2 meters per second. And despite the initial velocity difference, you can see that both have a terminal velocity around 2.37 meters per second. Now to conclusion, after going through the process of making observations on free fall motion and making two models to mimic the motion, these are my findings. Air resistance has significant impact on the motion of free falling systems, and a free falling system reaches terminal velocity when it reaches a velocity where the magnitude of drag force equals the magnitude of gravitational force.